Good morning, everyone. Welcome to A5X, the Ascent series. My name is Shahira, and I'll be your MC today. It's great to see a mix of founders, investors, ecosystem builders, and researchers in this room today. So A5X, the Ascent series, is a curated lead-up to NUS Enterprise's flagship event, the A5X Global Innovation and Venture Summit, happening this September. This series brings you closer to leaders who have already made the climb, individuals who have built through uncertainty, scaled breakthrough ideas, and navigated the realities of innovation at the highest level. Each session is designed to give you first-hand insights into what it truly takes to move the idea to impact. And today's speaker embodies this journey. Before we begin, please join me in welcoming Gary Ang, Professor of Practice for Defense Innovation and Applications, a champion of defense in entrepreneurship, and today's Q&A moderator. We owe a special thanks to Gary for his instrumental role in bringing our guest here today. Gary, the floor is yours.
All right. Thanks very much. Thanks everyone for being here. Our speaker is the kind of engineer who doesn't stop at publishing breakthroughs. He builds companies around them. And that's how I got to know him. He's the scientific advisor of Robos, an advanced manufacturing company that started by building parts for F1 cars. And that's why their first few investors were Ferrari and Fiat. And I'm the business advisor, and I got to know him through Zoom calls and all that. And I was very impressed by the kind of person he is, being able to bridge both sides, publishing papers and then translating them into scientific breakthroughs and into world-class companies. Professor Alberto Ortona trained in naval and mechanical engineering in Naples. So he's Italian, lives in the Swiss part of the Italian part of Switzerland, so the best of both worlds, in Lugano. He specialized in composites at the University of Delaware, and then spent a decade in industry before becoming full professor of SUPSI in Switzerland, where he now leads the hybrid materials lab and has over 30 national and European projects in space and aerospace and defense and everything else that you can think about, where ceramics and advanced material science are needed. He's a co-founder of NGSA, a faculty member at the University of Padova, and author of more than 100 papers and 10 international patents. Last year, he took home the Golden Star Award at the world's premier ceramics conference in Daytona Beach, where, they have the NASCAR races. 30 years of turning exotic materials into real industrial solutions. Today, he's going to show us exactly how that's done. Please welcome Professor Alberto Ortona.
First of all, thank you very much, Gary. You really made it this thing happen, and I'm very happy about that. I'm very happy to share today my experience in a field which is not so, let's say, trendy or famous as can be plastics or metals. But nevertheless, if you want to get some impressive performance of components, sometimes, especially if we are dealing with high temperatures, and by high temperatures I mean above 1000 degrees C, there are not too much choices. So ceramic materials become a sort of must-do. What I'm going to present you today is a combination of materials and shape in order to achieve particular properties in a sort of material which is called hybrid materials. It's a definition from Professor Ashby from Cambridge, in which you can combine materials to get the best, hopefully, from more than one material. In my case, in our case, normally we have one material which is a ceramic and the other material which is a gas. Can be air, can be plasma, can be whatever. And as you can see here from my presentation, I belong to a University of Applied Science, which is really a German way of looking at engineering. In Germany, in Austria, and in Switzerland, they have forever had these kind of universities in which we are not doing basic science, we are applying basic science into components or into systems. And that's why I'm very much close to companies, because normally I start from somebody's good idea, and I bring this idea into a component, which becomes a system later on. Before actually speaking about what I'm doing, I was, when I was asked from Gary to present something here, I tried to look what, because I was not very much aware of, what Singapore is doing as a country. And I found incredible similarities between Singapore and Switzerland, because they are both very small countries. Don't get misconfused by the fact that in Switzerland there are 40,000 square kilometers, and here there are only 730, because 70% of Switzerland is steep Alps, so it's useless, let's say. So the habitable territory is not that big. And beside that, they are, as Singapore, they are two small countries surrounded by larger countries. In Switzerland, Switzerland is not Europe. I don't know if you know that. It's a singular state. It's surrounded by the biggest European countries, but somehow over hundreds of years it managed to stay an independent country, and I guess Singapore is pretty much the same. Beside these, they are both rich countries with a very, very high trading business and stuff like that. Also politically they are very similar, and another very interesting thing, in Switzerland we speak 4 languages. One is Italian, one is French, one is German, and the one is, you probably don't know it, it's called Romansh. It's a mixture between Latin and German. It's a very weird language. So it's a very, let's say, mixture of cultures. So I was pretty much impressed. And the fact is that they are very top-level countries in terms of high tech, in terms of people, in terms of currency. Both countries need to do a lot of research to make to capitalize on human beings, because if you do something that somebody else does, since they are rich countries, since the income of people for people is higher in both cases, you don't pretty much get you're not competitive. So yeah, they have a very good trade and economies. They are very stable countries, and you have a lot of competitive, because here is this is the case. There are very famous universities like in Switzerland and here, which are continuously training highly skilled people. So this is the real richness of both countries. Okay, and the fact that they have 4 languages. So, I mean, I am very different from a guy from the north of Switzerland, because first of all he speaks German, but he is German in the way he thinks. I am Italian. I'm really Italian, but also the Italian people, the Italian-speaking people in Switzerland are Italian by culture. So this is I think this is a high, it's a richness. And we are both doing super high-tech entrepreneurship. I was reading that, Switzerland has the highest number of high-tech spin-off new companies coming out from ATH and FFL. I don't know if you know, these are the two biggest universities or technical institutes in Switzerland. They are producing by far small companies than all the other countries in the world. So talking about developing new ideas, I don't have to teach you this loop here, but it's a typical and wise way to transfer an idea into a real business. So you have an idea, you try to see if this idea has a market. First of all, you are trying to develop something to bring this to a market. You bring it to the market, you see if it works, you launch the product, and you start hopefully getting revenues out of it. So this is not my business, say. But what is my business? It's a very peculiar combination of material, which I call hybrid materials. And these are some of the application of these porous, let's call it porous or hybrid materials, whatever you want, in which by shaping the material into the space, you can get some special properties. For instance, you see, I've been very active in the aerospace field. For a long time, we were not active that much. 6 months ago, 1 year ago, the aerospace and defense business was ramping up like crazy. So we are back on business on that, and I will show you. And meanwhile, we were very much active on chemical engineering. This is a new trend, also called very much trendy in Europe, which is called process intensification. By using this porous material, you can enhance chemical processes and contain these processes into a very small volume. So you can contain volume, you can increase productivity, and you can do it using, for instance, electricity, which is very important in Europe for reducing CO2 and stuff like this. But I will show you real examples. And we also started with, let's say, the first reactor I was working with was so-called the porous burner, this one. It's a burner in which you don't have the classical free flame you can get from a nozzle. It's you let the gas flow into a porous material, and when this material ignites, it heats up the material, and so the material ignites the gas. But again, I will show you a real example out of this. This was very successful, and indeed this Engiser company was built around this idea. In the last years, this was no longer so effective because fossil fuels were going down. Right now, they are going up again. So, in new companies, the reality around a big company is also a very, very big business. Of course, an engineer cannot predict these kind of things. You need the other guys. But anyway, these are many different cases of all components we have done over the years, and I will go through this in more detail pretty soon. But what I want to try to let you, let's say, tune in with our concept is that we don't build a material, we don't build a part, we always build a flow of activities which brings from the necessity of what a component must do, brings a component which does exactly what you want. And by using porous material, you can do this. For instance, this is a heater, and in this heater, I want to heat as much gas as possible, so I need a lot of surface. These porous materials are perfect for that because they have what is called surface area, which is very wide. And with that, I can have the current passing through from one side to the other. And so you can do it with a standard porous materials, or you can design a porous material like this. And then with the computer simulation, you can obtain the best performance. So you can let the current flow where you want. And by Joule effect, you heat up your material. And then you can make simulation, optimize this. This is called the topology optimization. It's a very on-fashion thematic right now. Then what we do also, we compare simulation with real results in this case. So this is a real temperature distribution. This is the simulation. And at the end, we can produce this component, which, as I told you, is very much used for process enhancement. So let me show you some case study so you will see what I'm talking about when I talk about components. The first one is a porous burner. So you can see here, this is, as I told you, the gas will come from backward, will come toward you, let's say. Oops. Takes some time. You can hear also the noise changes. Right now, here we have 1,300 degrees C, 1,400. You see, it accelerates. Now, the thing is that you cannot do this with any other material but this, because it's a very oxidative environment, contains water because it's a combustion. And the thermal shock are incredible. I mean, it goes from, when you turn this off, it goes from 1,300 degrees C to 300 degrees C in 3-4 seconds. So it's really huge. And so there is only one material which to date can do this, and this is silicon carbide. And this is exactly what our expertise is about. Over the years, we moved from methane also. We are now working a lot on combustion of ammonia. Ammonia, it's a big business right now. Japan, it's really on it very much. They want to be independent from fossil fuels, so they are working a lot on ammonia combustion. So this is one case. Another case, and this is we get into the defense. This is not defense. This is aerospace. This was one of our first project on re-entry reusable vehicles. So this is a sandwich structure, all made of ceramics, which was meant to cover pretty much like the tiles of the space shuttle or the new vehicle from X. This is something like 20 years ago, and we filled this ceramic material with a foam and with another porous material in order to get insulation. And we placed here some titanium holders here. This is what we call the passive thermal protection. This is called the active thermal protection. This was another project, European project, like the one before, with the DLR and the ESA. And this is indeed, on the other hand, this is active protection. So we were flowing different gases in here. And so this was acting as a sandwich structure, but also through the gases flowing through the porous material, we were also removing the heat. And this was tested into a plasma wind tunnel, or DLR. This was Mach 7, Mach 8. So these are very high temperatures. And this structure survived like 30 re-entries. What happened at the end of this project? happened that ESA said, okay, I want to finalize all the ideas which are, let's say, flyable, say TRL-9 on, from TRL-9. So all the ideas which were at a lower TRL were sort of cut. And these things stopped, but as I will show you, we are back on business on that. But this was a very interesting idea. This is the business we are working on for 3-4 years right now. This is a mock-up of a reactor. Here you have this ceramic material, which is electrically conductive, thermally conductive, and acts as a support for catalytic reactions. In this case, we were flowing methane here, and we were cracking methane thanks to electricity. And from here, we were recovering high-quality carbon powders, carbon nanopowders, and hydrogen. So this idea is, for instance, this is a typical idea which started from TRL-1, and we are up now to TRL-3, and I will show you how we go on and on trying to reach a real production. This is very, very interesting because normally carbon black is produced by burning acetylene. So part of the acetylene brings the heat and the rest is decomposed. But you produce a lot of CO2. So all the big companies, when the CO2 was something really wrong to have, they pushed us to do this. But by the time we developed this, CO2 was no longer a big business. But from the latest news you can hear, now again in the last days, I was at a conference, at a trade fair yesterday, and again now renewable energies are getting a push because renewable energies right now means independence, energy independence. So everything is changing like a crazy in the last days. This is another idea, very interesting. In Switzerland, there is a lot of money spent not for renewable energies, but to reduce energy waste. So a lot of money is going into buildings and stuff like that. And a lot of money is going into getting from incinerators. We have, in Switzerland, there are something like 60 incinerators, a lot. Some of them are close to industrial companies, so the heat from these incinerators is used by companies as a process heat. But in other countries, in other places, this heat is not used that much, especially in summer. In winter, it's used to heat up houses, but in summer, it's not. And in this case, this heat will be used to produce chemicals, as I will show you. And we have a project right now between Korea and Switzerland, in which we are trying to make an heat exchanger like the one I showed you before, with a very thin walls made of a material which is called the ceramic matrix composite, which can bear high pressures and can be very effective in heat transfer. So this is something that companies in the chemical industry need, because to increase the productivity, you always need to have a high pressure. And so with the Korean Institute of Nuclear Energy, which are developing these special tubes, they have a very good knowledge on that. We are developing the porous material inside, and together we are developing this heat exchanger, which will be used for chemical reactions.
In the renewable future, we will have an excess of electricity in the summer. But in winter, when the sun shines less, there will be an electricity shortfall. We need to close this winter electricity gap. Power-to-X technologies are key to this. We can use them to convert surplus green electricity, heat, and CO2 into useful chemicals. For example, into hydrogen, methanol, and ammonia. This stored energy can be made accessible again in winter for electricity, heat, and the chemical industry. To get this concept to scale, we are building the GreenHub at the waste incineration plant Horgen. We have enough space here, and we can use heat from the plant to produce hydrogen much more efficiently. And when we convert the stored energy again in winter, heat can be fed directly into the district heating network. For this project, many research partners bring theoretical knowledge and testing experience into practice. That's how we are setting new international standards for our renewable future. GreenHub.
Now you start watching one of the biggest institutions which are helping new companies in Switzerland. It's called InnoSwiss. So this is an agency which brings idea from TRL 3, 4 up to 5, 7, and they give you money to develop this in a special way. I will tell you about that. We are in this consortium, and with this company, this is a huge company making ammonia plants. We are developing a process in which we want to decompose ammonia and produce hydrogen and nitrogen. And the idea is to use the heat from the incinerator to crack the molecule of ammonia. Why we want to do that? Because, again, this is a policy of, because ammonia is seen as an energy carrier, pretty much like oil. So you produce ammonia here and there in the world, you bring it somewhere, and then by cracking ammonia or burning ammonia directly, you can use this as an energy provider. So the idea is to use this kind of heat exchangers I was showing you before, even though if that's in another project, to produce this kind of fuel or energy storage. This is very well seen by Switzerland. So whenever you are dealing with these kind of things, and you have a startup, they will help you a lot because they think this is beneficial for the country. So this means independence, and Swiss made independence is flag over hundreds of years. No, so this is something again which is an opportunity for startups. And I will just finish with this project. We just got funded last week. This is, let's say, the final, for me, goal of hybrid materials. In this project, which is funded by ESA, which has Ariane Group as an end user, we will develop hybrid materials with a technique which is called computational design to engineer thermal protections with the different goals. And one of them, believe it or not, this was a goal from Ariane, is inspectability. So Ariane want to produce a thermal protection system. This is from SpaceX, but they wanted to produce thermal protection tiles which are very easy to inspect once the plane has landed, or the plane, or the spaceship, or whatever you want to call it. Because in the past with the space shuttle, and I don't know if you know that the tiles of the SpaceX are exactly the same of the tiles of the space shuttles. So they are a technology which is tens of years old. They have no way to inspect them easily. So Ariane really put this as a fundamental thing. So by playing with porosity, our goal is to find a way to let somebody easily understand once the airplane has landed or not, if that protection is can be used again or not. So now these are, let's say, what comes before, And now I will tell you a little bit about what comes after, which is some kind of enterprise around an idea. So the first company, and I was a co-founder of this company, was built around the idea of making an industrial porous burner, very easy to make. So everything you see here is really simple mechanical work. The only, let's say, very hot, not only in terms of temperature, but also in terms of technology part, is this ceramic part, which is inside the net. And these burners were used to produce high energy, high flux infrared heaters. Because these kind of burners are made of silicon carbide. Silicon carbide has a very high emissivity, so it can really produce a lot of heat by radiation. And the industrial product for this was paper drying. Believe it or not, when they produce paper, I've watched because we mounted the system right there. The paper, the pulp, when it becomes from the pulp to the dry paper, you have these rolls which are huge, immense, and they go at an incredible speed. I mean, meters per second, really. And so in order to heat up and dry this pulp in a roll which goes very fast, you need an intense heat. So one of the biggest problems of this heater is that if the system stops, because if the system stops, you burn everything. But shutting down this thing, it's quite easy and is feasible only because the material is silicon carbide. Because you just turn off the gas, because you have a mixture of gas and air, of course. If you turn off the gas, the air becomes a coolant, so the system immediately cools down, as you might have seen. And so this was developed with this company, which owns a patent on that, which also expired, I guess. All the tiles, all the ceramic tiles are produced by Engicer. So I mean, it's not a big company, but it makes quite a good revenue. A new project which is going on with the Thyssen Group. Thyssen Group is a steel producer in Germany. It's an incredible idea that a guy from Karlsruhe Institute of Technology had, and again to reduce emissions, to paint the coils, they use a paint which is diluted into an organic solvent. So the idea is to evaporate the organic solvent and use it as a fuel for the burner. And so you see here, this was one of the first tests. The big thing was to separate the part where the solvent evaporates from the part where the solvent burns. Of course, otherwise you will get a blast. And so it was not too much development of the burner, it was the development of a glass. Because it's really keen to melt, because it can develop very high temperatures. So it was produced a line, a very big line at Thyssen, and I don't know if it's running or not, but this is something which is really, I mean, Thyssen was very, very happy about that. And so this is the first case. Another case, as Gary introduced me, is we are developing a reactor from a new technology, let's call it, which uses robots, 3D printers. And this reactor will be made with their machine, with their materials, and after thermal treatment will become a reactor for process intensification and for production of hydrogen and methane. In this case, we are developing carbon material, not silicon carbide. But this thing is going on, and yeah, it's looking good. It's also because Robos has a very good capability of scaling up these things. So we can make a lot of parts or big parts with their machine. So now becomes probably the part most important for startuppers. How all the things I showed you are possible in Switzerland and in Europe in general. In Switzerland, we have 3 programs. So if you are starting with an idea, you can get money, but this is mainly for university. Can be everybody, eh? It's not necessarily a university, but normally it's in the university domain. If you are starting from TRL 1, you can get money, a lot of money. This is a very rich program from the Swiss National Foundation. If you have an idea which is in between a real product or just an idea, there is a program which is called Bridge, a bridge between TRL 1 and TRL 7. This is again quite a rich program. Can last up to 4 years, and they give you money to move forward, let's say. If you have a good idea which already you proved with the prototype, you can get money with InnoSwiss. Is the program I showed you before. InnoSwiss is very interesting. I mean, I've been in Italy, working in the US. I've never seen something like that. I work in Germany. I've never seen something like that. InnoSwiss works this way. I am a company, and I want to develop a new product. The government doesn't pay me, especially if I'm a startup or a very small enterprise. The government, the confederation actually, doesn't pay me. I have to find a university, and they pay the university to work for me. If the idea is sellable, I have all the rights. So it's like seed funding, I don't know, but without any scope other than getting people working, hiring new people, or paying taxes if this thing works. And this is exactly why we have so many startups in Switzerland, thanks to this InnoSwiss. This is very powerful. They spend a lot of money out of this. Yes. But we can get also money from Europe, because Switzerland is giving money to European community to be part of the European project. I'm pretty much sure you know that this is a big business in Europe. And we have several ways to get money from, let's say, from fundamental research, European Research Council, to accelerator. This is a special way of getting money if you are a small company. These are very similar to InnoSwiss. So AEC Pathfinder is a way to get money to bring ideas further on. And then also ASA is through many calls is helping companies in the aerospace or defense, trying to pass the, let's say, the problem of getting money before selling things. And finally, of course, European Horizon projects, which are very rich and brings together many companies with a goal. So, I mean, overall, this is a powerful way to help companies in Switzerland and in Europe. I must admit that this is shrinking. Lately, it's not like 5 years ago. We are getting cuts either from Switzerland and from European community, and the competition is incredibly high. I mean, imagine that the success rate of a European project is around 5%. So you are 10 people. You are 100 people and 5 get the money. So it's very competitive. nevertheless, there are chances. I mean, I've been part of many Horizon projects. Mainly, I've been part in the InnoSwiss project because the way University of Applied Science works. Okay, we are more close to the final product. Okay. So, if I have to give some advice, as both as a professor and as a former entrepreneur, what's important? Of course, I speak about Switzerland and Europe. Huh? First of all, you have to be good to sell ideas. When you have an idea, when you are a TRL 1. And that's not easy, I must admit. But this is something you have to do to convince. In our case, this selling idea means writing a project which somebody will fund. Once we are after this, we can try to sell. I call this architecture because in our case, these are distribution of materials into the space. And as I showed you, we were very lucky to find many ways of selling this distribution of material and space depending on the situation. When there was good for chemical industry, we were selling porous material for chemical industry. When it was good for aerospace, we were doing this for aerospace. And of course, at the end, you need to sell a solution. I mean, for instance, there was a ThyssenKrupp which was, I mean, they were very upset to heat up the solvent with methane and then burning into a chimney the solvent which was evaporating without doing anything out of it. So this was really a waste of energy and pollution, which more and more you cannot afford this. So in this case, together with other people, we were selling this solution to them, and fortunately we got the thing keep going. So how you do this? Well, at the beginning, it's not worth to spend a lot of money to try to demonstrate something which might not work. So it's better always to start probably with a university, probably thanks to some funding from agencies. You start to demonstrate the principle with the simulation, pretty much. Let me give it as a broad definition. In our case, because for us producing a digital file, it's easy. Simulating it's easy if you have partners which are good in doing this. And then if these things make sense, then you make it. And this is this is the combination that made our, let's say, proposal very much successful, I would say, yes. Because 20 years ago, I realized the powerful of additive manufacturing, which is not making bunnies or chassis pieces, which is typical, or Tour Eiffel. This is what you see when somebody trying to sell you a machine. You can close a loop. I mean, you can transform an idea into a piece right away. So this is very powerful. And if you do it right, this is really, you can do many things and you can satisfy many customers in our case. And then this is also probably the tough part for a company. You have to crush against the hard life. So it's not always the case that what you have done here works, but believe me, if you have done this right, these things is much easier. Let's put it this way, to be frank. Okay? So I think this is it on my side. I just want to thank my co-workers, my lab partners. And this is pretty much what I was saying to you. So we have my laboratory is now divided, let's say, in 3 pillars. One is computational design. it's really one business alone. So we are very good in producing these kind of 3D virtual objects, let's say, which we can give them to simulation people. And if they say it is right, we can print, we can make them ceramics, which is our, let's say, expertise. Of course, we have a good characterization, but I will bring this pillar together. And then lately, also because I realized that sometimes people don't get the best of what we have done before because simply they are not, they don't have the right mindset. So in the latest 3 years, we became very good also in producing systems, reactors, in which the novelty is this part, the porous part. The rest is something which is nothing special, let's say. But it's ancillary material, let's put it this way. So this became also a part alone, and as you saw, all the reactors, all the systems we developed was developed by a guy who's very good at, but works exactly in bringing all the stuff which is needed around our hybrid material to make it work. And I think that's it. I hope I was on time, and thank you very much.
All right, thank you, Professor Ortona, for that insightful sharing and very realistic advice. I wasn't aware how similar Switzerland and Singapore were structurally similar. But of course, you know, they have like 4 seasons, and Singapore still remains with 2 seasons, hot and humid. I'm still waiting for someone to do a research on that and commercialize that. To take the discussion further, we'll now move to a dialogue session. Let's welcome back Gary. Gary, over to you.
Okay, since I've got a mic, I'll do the first question, which is related to your point at the end. What do you mean by startup should only start after the technical risks are removed? Is that possible given that there are unknown risks and the applications keep evolving? And at what TRL should a startup start? Because if you look at robust is already TRL 9 and 10 for some of the products. And then with ceramics, it's 2 to 5.
Yes.
So this is more to seek clarification of what you actually mean.
Well,
because there's always risks, startups, and startups can't wait to start.
Well, with NGSER, we reached the production. So it was, let's call it TRL 9. An important thing is that also NGSER doesn't make all the money with porous burners. They have a lot of, say, other products. And they really sell products worldwide, depending on the application. The good point is that sometimes somebody, simply by watching a burner burning, get some spark inside his mind and brings him new ideas. But yes, not many of these examples are to TRL 9. I mean, some of them are the highest is TRL 7, something like that. And yeah, it's a hard job. And also another very important thing is what goes around the politics. For instance, right now the biggest problem of Switzerland is that the Swiss franc is incredibly high. So all the products which were costing 100 yesterday, today are costing 120. I mean, this is something you have to cope with. And if your product is unreplaceable, somebody will do the effort. If not, and the lower the technology you are developing, the higher is the risk to be crushed. I mean, so it's really, it's not easy, but I would say that thanks to this funding from companies, from agencies, these companies are doing, sometime are coming out with very, very good results. I mean, for instance, one of my former colleagues funded a company which is called Synelion. I don't know if you ever heard about that. They produce fuels from CO2 and from CO2 and water, and they use concentrated solar heat to make this reaction happening. Now, solar was going down, but this guy had a very good idea to combine solar heating with electrical heating. And since PV is getting very, very massive, especially in Germany, and since Germany is, the problem of Germany is having, they can have peak of extra energy which they don't know what to do. And in this case, they sell this extra energy to this company, and this energy is somehow stored into fuel. And this company now was financed by Swissair, which is claiming to use their fuel, which is, let's say, they call it net zero CO2.
Net zero, yeah.
So, I mean, that was a very good idea, and this company is going very well.
So when this company started, it was TRL, what, 7, 8, 9, or
yes,
around there. So that creates a kind of moat against potential competitors if you started later.
Yes, of course. If you start early, you are the first.
Would you say that applies mainly to material science companies, or generally most of the deep tech companies should adopt such a strategy?
Well, to material company, I can say. To deep tech in general, I'm not fully aware of all the other of what all the other companies do. But if you develop a new material and you are the first, you can, because again, it's not making a new material; it's making a material for a component.
For application.
Yes.
Yeah.
So if you combine the two, that's really an advantage, because also copying you, it takes time, and yeah.
Yeah. Questions from the floor.
So you mentioned about different stages where you build the science, and then stage 2, you build an architecture. Is there what would your advice be for scientists working in lab, maybe to plan ahead? How can we talk to different people, or some sort of feedback initially, so that if we want to do some translational research, that we build or direct our science in a way that it has a potential to do the translation? That's my advice.
In this, I'm quite sure of what I will tell you. Normally, scientists go to science conferences and meet other scientists, and this doesn't bring to any company. Builds up science, but that doesn't build up. Switzerland in this is very good. We have a lot of happenings in which this agency bring in companies. So you have few scientists, many companies. Sometimes nobody cares. Sometimes you build up a great business. So meeting different people is the key. Now, how it's, well, for instance, a situation like this would be ideal, no? So really, it's not just a matter, because there is a lot of incredible science out there. But I'm not sure that all this great science is a great company, becomes a great company, no? So, especially when it's industrial application, because probably in the software industry it's easier, no? Because you don't have to put all these things together. Here it's much more complicated, but definitely is worth the effort.
Why is it that great science does not become great companies? I mean, if you look at some of the most successful companies, they all came from great science. Semiconductors, space companies and all that.
Oh, yeah. Yeah, but
and
this is the tip of an iceberg for me.
so how would you recommend solving that other than bringing, business people and great scientists together? Is there a much more practical way? Because I think that has been tried. And I'm asking for self-interest because I'm a professor of practice. I'm supposed to, bring deep tech science into defense innovation and applications.
Yeah. In US, it's famous. There is the famous pitch elevator. You have to convince a guy in 10 seconds. But this again, you meet somebody and you have to be good to get in contact with him. And this depends very much on the person. For instance, Apple, the guy was an incredible seller. No, so. It is more institutionalized, I think you get more chances. This is because I see I'm telling you what I see in Switzerland.
So from your experience in Switzerland, is the limitation on the side of the scientists who cannot articulate his deep science to the business people, or is it that the business people are unable to understand, the opportunities, the potential of the deep science? What's your sense?
Well, I distinguish two kind of business people. I mean, normally you probably have you are a company. For instance, there is a famous company which is called Litos, which is the best producer of 3D printing machine, which came out from a PhD student in Vienna, and the guy was not trying to convince any financial institution. The guy went to another big company producing 3D printers, which is called EOS in Germany, and he convinced him to put some money on his business. So, yeah, there are two ways you can convince a guy which is from the real industry, like robots. They were convincing Fajin, which is a super guy. And another thing is to convince a financial institution, but a financial institution is risky because sooner or later they want the money back. I mean, this is normal. I mean, you cannot blame them. You need somebody who watch behind this and can understand. I think this is quite difficult, always.
What friction points do you see when you're trying to spin off out of the Switzerland ecosystem from a university, right? Because as you build more and more IP around bringing this to a higher TRL, right? What happens is that then you have a whole bunch of technology that needs to be then put into a company, right? So then you have this balance where you have built a lot of IP and then you spin off, there's potential encumbrances, right? In trying to get this IP out. I wonder what environment do you face in terms of licensing and so on in the Switzerland environment, right? That you can share with us, because we are thinking about this right now.
Normally, you are trying to develop something with an end user. This is more safe. So you sort of make a de-risking strategy, no? Of course, you probably get less revenues because you have to license to him and only to him for a certain application or for a certain time. But there are different ways. I mean, and it really depends on your product, because some products just go into the market right away, and some other needs building up IPs over IPs and getting better. So frankly speaking, I don't have the real answer to you.
But in your own experience, I mean, you have spun off companies, right? So
yes.
Do you feel there's some friction, or maybe there's no friction in this process at all?
Well, if your end user has a clear strategy, because because we are selling parts of a system normally, no? So the porous ceramic can be a part of a chemical reactor, can be a part of a burner. If the company can see a real business in producing, in improving its competitivity or refurbishing all the systems with your new component, there is no, it goes all the way to the final product.
The problem that I think that I have faced when trying to get a successful startup, especially for industrial context where you need something big like a pilot, is that typically those companies, those private companies, before they want to put money to build a pilot, they will ask you to have a pilot. They will ask you to have been able to demonstrate something out of the lab. So I think it becomes a chicken and egg problem in a way, where if you don't get this money, which typically if you want to build a pilot in industry, you may need $1 million. And then if they don't want to give $1 million because they want you to have proven that it works at industrial scale, but you cannot do an industrial scale without having the $1 million, then I have found that this is the key issues to get successful startups in my experience. I'd like to know your view on how to resolve this conundrum.
In this matter, I have a clear idea. Fortunately, in Switzerland and in Europe, there are means of getting a pilot without you paying for the pilot. I mean, you can be, for instance, with the pilot plan from which was a line along 50 meters. Of course, it was really a $1 million business. It was a refurbishing, but anyway, it was a lot of money. We got something like 7 million euros to do that, which is a fair share of budget to do that. So, of course, if you are all alone, you cannot do that. Unless you sell your soul, you cannot do that. Fortunately, in Europe and in Switzerland, if you convince the partner of your functionality of your part, you might be successful this way. So this is very helpful, because otherwise, really, it's. I totally agree with you, but in Europe there is this solution. Yeah.
Hey, Professor, thank you for your sharing. So I'm actually currently looking to commercialize a new material for hydrogel, and I think we are currently trying to cross the valley of death. And I think the first question is how, because the applications are very specific, how do the applications find you, or how you find the applications? And then the second piece is, I did a quick search that silicon carbide is actually a very readily available material. Mm-hmm. So what is the USP, or how do you protect your technology? Is it more of the design, the production process? Just wanting to figure that out as well. Thank you.
This is exactly why I am in a University of Applied Science. I didn't invent silicon carbide. We are inventing. Let's say we can master a process in which we shape silicon carbide in a given way to produce a component which does something that other components do not. So this is the answer of your second question. The answer to your first question is it is tough. You are a leaf in the ocean, and you have to find another leaf. So fortunately, to date, there are many ways to be known, like social, LinkedIn or whatever. Otherwise, again, if you know that there is a system that tries to monetize the money they put into the research, like I'm saying, like in Switzerland, this is very good. I mean, because you just go to these happenings, and you find a guy who watches your pitch, and you get in contact, and you go ahead with doing some business. Yeah, but it's tough.
Can I have one more? Just now you commented that you didn't invent silicon carbide, but the novelty is in the way that you're processing it anyway. So in one of your slides, you were writing, I saw written that you said that the know-how is embedded in the processes, not in the material. Is that what you meant?
Yes.
Okay, thank you very much.
Any more questions? Okay, if not, then we end with 5 quick fire questions. So I know he's a bit jet lagged, but this will keep you awake. One thing universities consistently get wrong about commercializing deep tech.
It depends on the university. Some universities are very good, like MIT. Some others are less good, and this also depends on how university are paid. Because if you get money from the government to make classes and teach other students, and you have no reason to make research, so you don't have the fire underneath your feet. This is one thing, and if you rely only on companies, that's another thing.
Okay. This is quick fire, so you guys need to give a couple of words or sentence, or one sentence. Best piece of advice you give a researcher standing at the door of their first spin-out?
Mingle, in general. It's very important. I studied at the University of Naples, and there was a professor of I don't know the English name, fracture mechanics, something like that. He was saying it's not important what you know; it's important what you sell, how you sell your knowledge. And said from a professor. I was at the second year. It was quite impressive to me. You know, I mean, I was not ready for this attitude, and indeed, it's very important. It's very important.
Biggest potential market for porous ceramics?
Right now.
Yes,
Defense.
right now. Defense. Okay.
No, because for instance, when there is an urgency, people doesn't care how much you pay.
Okay. What aspect of defense are you talking about? Because it's a wide area.
Everything that goes very hot.
In defense, it's either go very hot or very cold. Okay, this one is a bit of a loaded question. Switzerland or Singapore, whose innovation ecosystem has the edge, and why?
Well, I don't know very much about Singapore.
You just give a presentation on Singapore.
No, I mean, this was how I was surprised about Singapore. In Singapore, you have very good universities. I mean, the two technical universities you have are doing really well. And I must say that Singapore, as Switzerland, has the fire under their feet, because if you don't bring smart people with smart ideas, you don't survive. So, like Switzerland, it's pretty much the same.
Okay, last one.
Once Switzerland was surviving on banks, now not anymore. So.
Now on defense.
Yeah, I don't know.
Build your own. You've spent 30 years reducing technical risks. What risks have you never been able to engineer away?
One risk?
What risks have you never been able to engineer away?
I would say the unknown, but for instance, we were developing incredible burners which were sold like crazy with Gendicer, and all of a sudden methane was no longer a fuel. So, for instance,
Because of sustainability and all that.
right? Because of the electric cars.
I see. Okay.
Yeah. So it's really, but this is not only for ceramics. This is for everything. I mean, politics, and indeed, this is probably good for Singapore, like Switzerland. They have a very stable governments, and this is super important. You can see in US, no. US. I was speaking with the people from Department of Energy. They were super rich, doing super things. When Trump came in, they all stopped. This is not good. I mean, yeah, you can argue on that, but
Yeah.
it doesn't help.
Never take your research grant for granted. On that note, please join me in thanking Professor Alberto Ortona.
Thank you.